Okay, here's another topic that we're going to talk about today. It's taking a bit of a backseat again, but you kind of need the principles in order to understand some of the other things that will be happening later on in class, and it's got to do with buffers. So I'm on page 229 of your notes. We're only going to take a qualitative approach to this, so some of your notes can disappear. Before that, there was a note on the common ion effect. I'm not going to go through that either, so you can ignore that. Page 229, what's a buffer? A buffer is a chemical substance that will minimize the pH change when small amounts of acids or bases are added. Okay, so that the key there is minimize. It will change the pH a little bit if you add an acid or base, but not that much, and only if you add small amounts. You can't add a truckload of acid or base and expect a buffer to keep up with it. There's a little bit of where the word buffer came from in your notes. Blood, you might know, is buffered to a pH of 7.4, and if it gets outside that number, I'm not quite sure by how much, maybe the biologists know, you start to hyperventilate. And the old treatment for hyperventilation used to be to breathe into a paper bag, and the idea being that you would inhale some carbon dioxide, and it's a carbonate buffer, and so you'd get your buffer back into the correct range, and you'd be okay again. Buffers are usually made, we're going to talk about another way of making them in a few minutes, and buffers are usually made by adding a weak acid and its salt. So for instance, acetic acid and acetate, or it could be a weak base like ammonia and an ammonium salt or something of that nature. They can also be made by partially neutralizing an acid or a weak acid or its base. Concentrations are relatively high when compared to the concentration of acids and bases that are added. Addition of small amounts of acid base will not affect the pH very much. Okay, so I've said that before. Here's the qualitative approach. If I just took acetic acid and I dissolve it in water, I get a little bit of hydronium ion and I get a little bit of acetate. But we know from our previous research that the concentration here is really low. Okay, a really low concentration. So if I add acid or base or acetate or anything, there's not really much to work with on this side. Okay, if I added some H3O, if I had some hydrochloric acid or something like that, we would disturb the pH of this solution because I don't have anything for Le Chatelier's principle to work on. There's just not much of this stuff here. But everything changes if I have a concentration of acid here and I add an acetate salt such that I have something here. Let's just take a look at that. If I have acetic acid, so I've added some of this, and I've added an acetate salt, sodium acetate, for instance, which we learned in the previous lesson, will hydrolyze. If I add a strong acid, so I add some H3O+, you know from your Le Chatelier's principle that the equilibrium should shift this way, thus reducing the hydronium ion concentration, or bringing the pH back down, back to a position where it used to be. Okay, so that's how it works. The fact that there is some there. Up here, nothing there to work with, but by adding the salt, we give it something to work towards moving the equilibrium back to the left. Similarly, if I add base, for instance, if I add OH minus, I'm going to neutralize my H3O+ and form water. Well, I could look at this in two ways. I could say, well, if my water concentration goes up, I'm going to drive the equilibrium that way. But the reaction will take place. It tends to replace the H3O+, and thus keeps the pH at roughly the same concentration, or pH at roughly the same level. So that's the qualitative approach, and I think right now that's all you're going to need for what we're going to do. So if we flip the page and you look at page 230, we could do some calculations and stuff like that, but I think I'm just going to leave that out. There's kind of a nifty equation here that you go, and I think in your notes they put in something called the Henderson-Hasselbalch equation, but for now I'm just going to leave that out. We're not going to follow that too much. I just need you to know that a buffering system would be a weak acid and its salt, or a weak base and its salt. Okay. Again, this information here, how would you choose a buffering system? You're going to choose a buffering system through calculations where the Ka or Kb or whichever you're working with is going to be similar. The pKa and the pKb should be somewhat similar to the pH that you're looking for. There are reasons for that, but again, I think we'll just forget about this stuff for now. There are a couple questions from some of the really old exams that I'll just bring your attention to. For Mayo 2, it says, which of the following combinations will form a buffer solution? So let's take a look at the first one. 20 centimeters of 0.1 molar acetic acid and 10 mils of sodium acetate. So you'd look at that and you'd say, okay, it's the acid and it's salt. So I would say, yep, that one's going to work. Part 2, you say 20 cubic centimeters of 0.1 molar acetic acid. So there's the weak acid, 10 centimeters of NaOH. Now, don't foolishly look at this and say, well, this is not a weak, this is not the salt, this is not a weak salt of sodium acetate. But if we look at that, let's look at what's going to happen here. If I take CH3, COOH, and sodium hydroxide, I'm going to get CH3COO. Oh, look at that. There's the salt of a weak acid and H2O. We've done a neutralization. Let's look at the amounts here. I have 20 centimeters of 0.1 and 10 centimeters of 0.1. So I'm going to have half of this left over, and I'm going to have the salt. So this actually will make a buffer. Okay, so you got to watch out for that, and we're going to come across this when we talk about pH curves in about a day's time. Okay, so just watch out for that. Don't get fooled by the fact that this is not the salt of acetic acid. It can do the job. And here's another one. What's the buffer solution? 0.1 molar HCl and NaCl. Well, that doesn't work. That's a strong acid and it's salt, but they're strong, and so they don't buffer. And here we have acetic acid and sodium acetate, so it would work. So if we go through that, you'd say, well, the only answer there is B. Oh, sorry, we never did answer this question up here, but it would be C. Okay, so there's just a little word on buffers right now. So I hope you get something out of that.